be done as a whole. Okay. So collectively, I can say this much amount are the stray losses. But the problem is I cannot find all these losses individually. Yeah, like I told yesterday, there are losses in the uh, and stray losses not only consist of the losses because of these harmonics and all. Mechanical losses and iron losses are also the part of stray losses. Okay. So stray losses means all the losses those are existing in the machine when the machine is under load condition, except these copper losses. Okay, so copper losses are very much predictable. I know the current, I know the resistance of the winding, I can calculate. So copper losses are predictable losses, but whereas stray losses, they are not. As a whole, collectively, I can find the value of stray losses in the entire machine, but it is very difficult to find what is the exact amount of loss in the bearings, exact amount of losses in the shaft, exact amount of losses in the brush holders, what are the exact amount of losses due to harmonics in the flux wave at the teeth. So these are very difficult to find out. So collectively, I call it as stray losses because they are strayly existing in the motor. The name itself is telling that they are stray losses. Okay. In any part of the motor or the generator, they can exist. Okay. So generally, when we are studying the losses, we study the losses which are highly predictable, like iron loss, copper loss, okay, mechanical loss. We can predict them, we can calculate them. But when actually the machines are put into the service or on the load, most of the different types of losses will get into the picture. Okay, so practical behavior of the machine is completely different from the theoretical behavior what we predict with characteristics or with the performance values what we get. Okay, so such kind of losses are known as stray losses. Okay. So we have seen the Hopkinson test connection. Okay, and also we have seen why it is called a regenerative test or back-to-back test. Okay, so here a motor and generator are mechanically coupled. Yeah, or generally we can say two DC machines are mechanically coupled. Okay, and one is made to operate as motor, other is made to operate as generator. Okay, how we are doing that? We are doing that by weakening the field and strengthening the field. Okay, the field of the machine which is weakened will act as motor. The field of the machine which is strengthened will act as generator. Okay, so with weakening the field, I get more speed because speed is inversely proportional to flux. So when I weaken the flux, speed will increase. That is, it will give more mechanical output. When I strengthen the field, induced EMF increases. Therefore, that will act as generator. So one is giving out mechanical output, other is giving out electrical output, and these two outputs are connected back to back. So mechanical output is connected to generator as input, electrical output of generator is connected to motor as input to the motor. So hence this is known as back-to-back connection or back-to-back test also. And motor is utilizing the power given by generator to produce its output. That is in turn given to generator. And generator is utilizing that input to produce the electrical output, which is given to motor again. So the production of outputs are in this loop only. The production of outputs are in this loop of motor and generator. Hence it is known as regenerative test. Okay, hence it is known as regenerative test. Okay, so what we are doing in Hopkinson test, we are using two identical machines. So with the two identical machines, we are making one machine to operate as motor, other machine to operate as generator. And we are following certain process, certain procedure to find out the losses and then to calculate the efficiency. Okay, so since motor is acting as load on generator and generator is acting as load on motor, this is also known as direct test or load test. Okay, and I can operate this system at any load condition, not only necessarily at full load. Okay, by varying the excitation of both the motor and generator, I can operate the system at any load condition. That is one more advantage. It is not only at full load. Okay, but generally we take values at full load because I want to know what is the maximum amount of losses that can occur in the machines. Okay, and what is the output at full load condition, rated output, what is the rated efficiency, that is what I want to know. Okay, but practically we can calculate the efficiency of motor and generator even at partial load conditions also. Okay, so up to this point we had seen in the previous session. Okay, and if uh, the machine were not having the losses, okay, then whatever the output produced by motor given to generator, output produced by generator given to motor was sufficient to run this system forever. Okay, after the first excitation from the supply, we would have taken out the supply, but because losses exist in both the machines, that is not possible. That we have seen here in this point, that after some time, because of the losses, the power produced by the machines will go on decreasing at one point machine operating stops. So therefore, there should be continuous supply of input power to this system, to this MG set. This is MG set, motor generator set. Okay, so there should be a continuous supply of power from the external source to this MG set, so that only the losses, only the amount of losses are satisfied in both the machines. So the power required for the motor operation is given by generator. Power required for generator output is given by the motor. But because of the losses are existing, the power developed by the motor to the generator is insufficient, and vice versa. Therefore, the amount of power drawn from the supply is exactly equal to the amount of losses that are occurring in both the machines. So whatever the power is drawn from the supply is equal to the losses. Whatever the power drawn from the supply is equal to the losses. Okay, if losses were not there in the machines, then I would have taken out the power after the first excitation. Once the machine started running at their speeds, I would have taken out the power. But because of losses, I have to keep it. Okay. So this is up to what we have seen in the yesterday's class. Okay. Now, let me give the current values here. I will be following the current nomenclature, what is there in the lab manual, because it will be helpful for you in calculations. Okay. Even in my notes, I have used the currents that I have used, that is updated notes. Okay. The current nomenclature and the current naming is as per the lab manual. There should not be any confusion. Okay. So this current is I1. Let me take different colors here. I1. This current is I2. This current is I3. And this current is I4. So at this point, I1 meets I2 meets. So this current will be I1 plus I2. And this current is I2 plus I4. And what about this current? This motor will take the current, right? I will write down here. So it is I1 plus I2 minus I3. Okay. So the current nomenclature is exactly as in the lab manual. So it will be easy for you to refer and do the calculations shown in the records. Okay. So next we'll move to the operation of Hopkinson test. Okay. Operation. I will redraw the circuit here again. So there is a mechanical coupling. In the circuit diagram in lab manual, this switch is down here. Okay. So whether you keep it up or down, it will be the same. And don't get confused there. So this is the supply voltage V. Current I1. This is switch S. Okay, so this is current I2, I4. This is I3. This is I1 plus I2. This is I1 plus I2 minus I3. This is I2 plus I4. Okay. Here, or time being, I will just remove these currents because some more diagram things I have to show here. Okay. I will write down here. Okay, so here let it be I1 plus I2 minus I3. Now we know that one machine is motor, other motor is generator. So I will turn on the supply. Okay, I will switch on the supply and I will reduce the excitation of the machine. Let this be RHF, RHM, and this is RHG. I will increase the value of motor rheostat in the field and the excitation is decreased. Then this motor starts operating, running. Okay, and initially the switch S is kept open. Okay, initially keep switch S open. Okay, why? Because I have to connect motor and generator in parallel electrically. No doubt I have coupled them mechanically. No doubt I have coupled them mechanically. Also, I have to connect this motor and generator in parallel electrically. So when I have to connect two circuits in parallel, the voltages must be equal. Okay. No doubt the motor voltage is equal to V volts when it is turned on. But generator voltage is not V volts. It has not yet generated this amount of voltage. So what I have to do is, first I have to excite the generator such that it will give out the equal voltage as that of motor terminal value. Then I have to close the switch so that motor and generator will get connected in parallel. If I do that before, now suppose I have given supply voltage equal to 200 volts, motor is running at certain speed, say suppose 1000 RPM, generator is also running at 1000 RPM, and initially the excitation resistance or the field resistance of generator is kept large. Therefore, the flux in the generator field is very much minimum. Therefore, the EMF induced by the generator is minimum. So here there is 200 volts, suppose, and here there is say suppose 50 volts. What is the potential difference? It is 150 volts. So 150 volt is existing across this loop against the minimum resistance of armature. The armature resistance is hardly 1 ohm. So 1 ohm plus 1 ohm is 2 ohms. So in this loop, there is 150 volt against 2 ohms. What will be the current? 75 amperes. So these motors will be carrying 75 amperes of large current, which is also not a load current. That is a short circuit current. That will create a dead short circuit between two armatures of the machines, where it is also known as circulating current in the loop. Okay. So there should never be the circulating current in this loop. The current flowing between motor and generator in this loop should be always a zero. Okay. Or else it will create short circuit. So how to make it zero? So that the potential difference between motor and generator terminal should be equal. So that is ensured from this voltmeter. When I excite the generator and this voltmeter shows zero, it ensures that both the terminals are at equal potential. Then I have to close the switch. So initially the switch yes should be kept open. Okay. So when keeping the switch as open, okay, then I will turn on the machine. Okay. We'll start the motor. Start the motor. Either you can use a motor starter or you can use rheostats. Okay. So start the motor and bring to rated speed. Using RHM. Using motor field rheostat. Okay. Using motor field rheostat. Okay. Now here, observe the value of voltmeter. Once I make the motor run at rated speed, once I make the motor run at rated speed, just a second. Okay. Once you make the motor run at rated speed, observe the value of this voltmeter which is connected across the switch. If this voltmeter is showing 0 volts, then it indicates that motor and generator are at equal voltages at their terminals. If this voltmeter is showing some value, then that is the potential difference between motor and generator terminals, which should not exist. Then what should I do? If voltmeter shows 0, okay, start the motor and bring to rated speed using RHM. Okay, next, observe voltmeter across the switches. Observe voltmeter across switch yes. If it shows some voltage, okay, so this implies motor and generator are at different voltages. Motor and generator are at different voltages. But when I have to connect this motor and generator in parallel, both voltages must be equal. So it is not a passive circuit. Okay. In passive circuit, what will happen? As I go on adding the things in parallel, automatically the voltage will become equal to the source voltage. But this is not a passive circuit. Both are active circuits. Both are active devices. Okay. So therefore, one is the supply voltage, other is the generated voltage, which are connected to the same node. So it is very important for me that when I am connecting any two active sources or active devices or active components or active elements in parallel, the voltages must be equated. The same process you will follow even in the synchronization of your alternator using it to the bus bar. You did this. Okay, you did the same thing. Until and unless my incoming generator voltage was equal to the infinite bus bar voltage, I never closed the synchronizing switch. There you checked four conditions, right? Okay, that frequency should be same, voltage should be same, phase and phase sequence should be same. Okay, that we did with some other technique. But what actually we were doing, we were matching all the attributes of the incoming power with respect to the busbar power, the voltage, phase sequence, frequency. These are the attributes of incoming power or any AC power. So when they are matched, then only I can connect to the same node. Now what would happen if there would have been a difference between generated voltage and the busbar voltage? Again, there would have formed a loop between armature of the generator and the busbar, and that loop would carry large current. So same thing happens here. Now, if voltmeter is showing some voltage, it means motor and generator are at different voltages. Then what should I do? Then excite the generator, using RHG. It means decrease RHG and increase the excitation. Excite the generator or increase, okay, fine. Excite the generator using RHG until generator develops, voltage equal to supply value. Why supply voltage? Because here at this node, the voltage is supply voltage only. Directly it is connected across the supply. Okay. Then how we will ensure this? I haven't connected any voltmeter across generator. Okay. It is ensured when voltmeter across a switch shows 0. Okay. When the voltmeter across the switch shows 0, it is ensured that both the machines are at the same voltage or equal voltage. Okay. Thus, motor and generator now are at equal voltages. Okay. And close the switch, yes. Okay, so when voltmeter shows 0, then only close the switches. If voltmeter shows non-zero, and if you close the switches, then that potential difference will exist in this loop. Okay, it will exist in this loop, and it will make the circulating current IC. If potential difference is very large, IC will be very large, which may go to damage the windings. Okay. Now, if IC is very small, say it will not damage the windings, the potential difference is very less, but I close the switch. What will be its effect? It will not physically damage the machines. It will damage the performance. Okay. So how much I can load machines? Up to its rated current, right? Always we have seen machine should be always loaded up to their rated currents. Now what will happen? Suppose the rated current of motor is 10 amps, even for generator is also 10 amps, say, because they are identical. So IL is say 10 amps or IA load is say 10 amps for both motor and generator. And circulating current is say 3 amps. Okay. Now if you load the machines until their armature currents is 10 amps, then the actual current drawn by the or circulated in the armature of the machines is 10 plus 3, 13 amps, which is a overload current, which I will not see it coming. This 3 amperes of circulating current is very hard to measure. I cannot measure that. It is difficult to measure. Okay. Now, if you load the machines up to their rated currents, then additional circulating current is also flowing. So even when the motor is at its full load, it is always overloaded, both the machines. To avoid that, what should I do? The maximum current carried by the armature should be only 10 amperes. Then I have to load the machine only up to IA equals to 7 amperes. So if the current drawn by the armature or current developed by the armature in generator is less than its full load value, what is the power developed? Decreases or remains same? If armature current is less, what is the power developed by the machines?
Decreases.
Decreases. So what is happening here? Because of this circulating current existing, the load handling capacity of the machines have decreased. It is decreased. With the existence of circulating current, okay, the load handling capacity of the machine decreases. If the circulating current is very large, it will damage. But even if circulating current is not of that value, which will damage the machines, but still it will hamper the performance. So circulating currents are always harmful either for the health of the machine or for the performance of the machine. So I should avoid these circulating currents. How do I avoid that? By exciting the generator until this voltmeter shows 0. So when the voltmeter across the switch shows 0, it is 100% sure that the circulating current will be 0 because both are at equipotential. Then the circulating current becomes 0. There is no potential difference between motor and generator armatures. Hence, the circulating current will be 0. When I start loading the machines, only the load current flows in both armatures. Okay, so circulating currents, though they may not be damaging the system physically, but they will always decrease the load handling capacity of the machines. The same thing is also true in alternators when they are synchronized. Okay, the same thing is also true in alternators when they are to be synchronized. So always we should avoid the circulating currents, which will always hamper the load handling capacity. Okay. Yes. Now, when motor and generator, or you can say note we will take here, we will write a note. Okay. If armature voltages of motor and generator are different, the potential difference between them create circulating currents which reduce, which may damage armature windings. Why? Because armature resistance is very small. Practically, it will be less than an ohm. So when the potential difference of hundreds of volts is against less than a ohm resistor, then hundreds of amperes of current will flow, which is sufficient to damage the armature winding. Okay? Which may damage armature winding if have large value. Even if circulating currents are of low value, even if circulating current is of low value, not R, is of low value, it will reduce the load handling capacity of machines. It will reduce the load handling capacity of machines. Okay. So always machines have to be operated at under load condition, which will affect the efficiency of the machine. Okay. See, these kind of explanations will not be given in any of the textbooks. They may just say in one statement somewhere that if circulating current exists, they will affect the load handling capacity. But how they exactly will affect the load handling capacity can be explained only in the lectures. So class lectures are very, very important in understanding anything. Self-study is also useful and valid, but self-study needs a lot of determination and lot of insightness in the subject. Okay, lot of basics. Basics should be 100% strong. Then only you can go for self-study. Or else, lecture class lectures are the biggest boons to you people. So attentiveness in the class will clear so many doubts of yours, and it will also help in understanding almost everything that you study. So you have to practice to be attentive in the class. You should practice that. It will not come automatically. Okay. To be getting attentiveness in the class, you should practice it. Okay. So class lectures are very, very important in understanding any subject. Okay. So these all explanation, whatever I have explained just now about circulating current, I cannot put everything in the words. Then I form a notes and all. No, it is not possible for any person. But in the class, whenever I will be giving the lecture, in at any extent I can explain. Okay. So class lectures are very, very important. Now, this is one point. And then how to load now? That is the next point. The first thing is how to start the machine and make one operate as motor and one operate as generator. Now I started the machines. I decreased the excitation of one machine, that is motor. I increased the excitation of other machine, that is generator. Now I have made motor run at rated speed, generator develop rated voltage. Now I have to load these two because this is a full load operation. Okay. Now how to load this? Okay. Loading is, I am not adding any external load into that. Okay. The machines are loaded by varying the field rheostats of both the machines. Okay. Now, next step. Now, both machines can be loaded. Now, both machines can be loaded by varying field rheostats. By varying field rheostat. How to vary? That is important. Most of the students will make mistake here only in practicals. Okay, varying in the sense it can be increased or it can be decreased. Okay, but which has to be increased, which has to be decreased? That is important. Okay, if I want to load the motor, how can I load the motor? The load on the motor is generator, is it? Generator is the load on motor. When I say motor is loaded, when I make generator to develop more power. When generator starts developing more power, motor, it starts demanding more power from the motor. Is it? You are studying EPG now, right? Is hydroelectric power plant done in the class? I think now already you are in the fourth module. That has been done, I think. Yes?
Yes, sir.
Yes, sir.
Slightly we will go there because it is a concept of generator. Now I have a generator here which is connected to a turbine in a hydroelectric plant. Okay, this is not a Sudarshan Chakra of Krishna. Now water is falling here on the turbine. Okay, from the penstock. Now water falls on the turbine rotates, generator rotates, and it will generate energy. Now this I will take only two lines, okay, phase and neutral, single phase operation. Now this is connected to a load, any load. Now what is exact operation of the generator here? When the load is at some constant value, generator is giving some constant current, IL. I will not show field and all these things separately. Okay. Generator will produce constant value of the current. Now when I increase the load, what I expect? Now I have increased the load, RL2. What I expect? I expect more current. Are we willing to understand the concept or should I simply finish my work and get lost? Go to hell. So now both machines can be, if you don't respond, then I will cut short most of the explanation and just tell what is there in the syllabus and I will leave. Okay. Your response matters a lot in any class. This is on record, I am telling. If you are not responsive enough in the class, then I will lose my interest. And when a teacher loses his interest, then you people are doomed. One thing you should understand, you people don't know whether I am teaching right things or wrong things. You are so much dumb fellows, first of all. Even if I teach entire wrong things of Hopkinson test, you will never get to know, even if you write the exam, because you never analyze the things. You simply listen and leave. So when I'm asking something to you, it means that I'm expecting some response from your side. So that I am ensured that there is a connectivity established between you and me and I can go further. If you have buried your tongues in your throat, then there is of no use of all these kind of discussions. Yeah. Now we'll see how the motor and generator are loaded. Rest part is your fate, whether you want to understand or leave it. I am not taken the entire in charge of your understanding of the entire electrical concepts. Okay? And you people don't deserve good teachers. This is very well established fact. Your class fellows, your entire fourth semester current class don't deserve good teachers. You may be laughing at me right now, but you will repent for this when you go for seventh semester placements. And none of my such words have become wrong so far in my 15 years of experience. Okay, you will repent and you will sit and cry in your houses for not being able to answer even the simplest question in your interviews or in exams, wherever you go. Okay, and please remember, I am giving this all explanation not based on these concepts. I have already evaluated you in your previous external lab examinations, where you were unable to answer even Faraday's laws. Out of 67 who appeared for the lab exams, none of the people have stated even Faraday's laws correctly, who have studied generators and transformers for the entire semester. Keeping that level of your knowledge in my mind, I am giving all this detailed explanation. Or else by this time, I would have also entered, finished module 3. If you just open the textbooks and see the explanation, there is nothing. Half a page explanations are there. And this will be recorded. I will upload this video as it is only. Let everybody will also listen on YouTube to whom we are teaching. Let this become a troll. Let this become a meme. I don't mind. Am I audible or not? At least, or connection is lost.
Yes, sir.
Ah, good. At least you responded to this. Now, both the machines can be loaded by varying field rheostats. Okay. This is all of no use for you. You don't want anything extra aside from your VTU syllabus. So we will cater only VTU syllabus. You will repent when you study machine design in next semester. I will tell you. You will not understand even 10% of that subject if you neglect third sem and fourth sem machine subjects. And without understanding that subject, you cannot pass that. Okay. Now, the machines are loaded either by decreasing motor field rheostat or by increasing generator field rheostat. Now, why can't I increase motor field rheostat and decrease generator field rheostat? You figure it out because already you have studied generators. What happens when the generator excitation is increased? What all changes will happen in the generator? You already have studied in detail in your third semester and you have passed the exam. You figure it out. Okay, because in this syllabus, it is given only these two statements. Okay. So, till what value I have to vary this? The machines are loaded either by decreasing motor field rheostat or by increasing generator field rheostat until the machines carry rated current. Until the machines carry rated current. So when the machine starts carrying rated current, that ensures the full load condition of the machines. Okay, that ensures the full load condition of the machines. Now in this mode, we are like already I have mentioned that the generator is taking input from the motor and motor is taking input from the generator. So these two are taking powers from each other to develop the output, and the amount of power that is required to satisfy the losses in both the machines are taken from the supply. Okay. So in this way, this Hopkinson test system, MG set, will operate, okay, on the full load condition. It can be operated at the partial load condition also. Now, if I vary this rheostats at under load conditions, that before the rated current is carried, that is a partial load condition. So one advantage of this testing method is that I can test the machine performance at full load as well as at partial load. Okay, so this is one advantage of this. Now, already we have seen the operation. Now we have to see the analysis. Then how I can get the efficiency losses from this system. Okay, so there are two ways of calculating efficiencies. Okay, so first way, overall efficiency first method, we assuming efficiency of both machines equal. Assuming efficiency of both machines equal. Okay. So from the circuit diagram, you can observe here, I1 is the line current drawn from the supply. Okay. So let us write, let I1 is the line current drawn from supply. Then I2 is the line current of generator. You can observe. See, this is generator. Armature plus field. As per this connection is generator. Armature of motor plus field. As per this connection is motor. So when I say motor, this is the motor. Motor doesn't mean only the armature. So this is motor. Field plus armature is generator because these are shunt connected. Okay, these are both the motor and generator are self-excited. So when I say motor, it is field plus armature. In this connection, there is an alternative connection with which the meaning differs. So I'm telling in this connection, motor means armature and field. Generator means armature and field. Okay. So I1 is the line current drawn from the supply, whereas I2 is the line current of generator. Okay. So from the circuit diagram, I2 is the line current of generator. Okay. I3 is motor field current. You can observe I3 is motor field current. I4 is generator field current. It is generator field current. Okay. So line current of motor is from the circuit diagram observe. Now this is the motor. So line current of motor is this current which is coming into the motor, that is including armature and field, which is equals to I1 plus I2. Motor line current is equals to I1 plus I2. Okay. Then motor armature current. Motor armature current is out of I1 plus I2, I3 value is flowing into the field. So the remaining current is I1 plus I2 minus I3. And if you show different currents in the circuit diagram and same equations for the analysis will also be wrong, circuit diagram will also be wrong. You will lose almost whole marks. You should be careful in this calculations. Okay. Now, what is motor input? Armature current of motor. Generator armature current. Generator armature current is, can observe, I2 is line current, I4 is field current. So armature current will be I2 plus I4. Okay. It is I2 plus I4. Therefore, motor input power. Motor always takes electric input. So motor input power is equals to V into what is motor line current? It is I1 plus I2. V into I1 plus I2 is the motor input power. Now what is generator output power? It is V into line current. It is I2. Okay. Already we have assumed efficiencies of both machines equal. Okay. Already we have assumed efficiencies of both machines equal. So with that, the output of motor output is equals to, I can write efficiency into motor input. Okay. And which is equals to, what is motor input? We have efficiency into I1 plus I2. Sorry. Yeah. Into V. Because both are equal efficiencies, whatever the output is developed by the motor is the input to generator, equals to input to generator. Okay. So what is generator output? Generator output is equals to, I can write efficiency into generator input. Or I can write efficiency into generator input is nothing but motor output. Is efficiency into motor output. What is motor output? Efficiency into I1 plus V into I1 plus I2. Now what is generator output? It is V into I2. So V and V will cancel here. Therefore, efficiency is equals to under root, okay, I2 divided by I1 plus I2. I can write this as under root. What is I2? I2 is the line current of generator. What is I1 plus I2? Line current of motor. So I can write efficiency equal to under root generator line current divided by motor line current. So this is the efficiency of each machine, because I have assumed the efficiency of both machines are equal, which will not be possible practically. So this analysis, what I have done now, is only theoretically. Practically, this is not fully valid, because both machine efficiencies cannot be equal. Even if there are equal copper losses, even if there are equal iron losses, the total stray losses will remain different, because there can't be two machine parts which are exactly identical by size, by their nature, by their characteristic, and by their performance. We can't get that. Therefore, machines' efficiencies will differ. And one more problem with this kind of analysis is I can't find what is the loss. Directly, I'm getting efficiency without finding the losses. Okay. So with this, I cannot determine the temperature rise, because once I got to know the losses, I can determine temperature rise. So with these values of efficiency, I cannot determine the temperature rise. So this we hardly use for any machine efficiency performance evaluation. Okay. So we have to find the efficiencies of motor and generator separately. We have to find the efficiencies of motor and generator separately. So for that, we have to look into another analysis. Okay, that we will take in the third hour. So third hour, we have power generation, I will be engaging that class. Okay, because many classes I have lost when I was not well. So I will regain those classes in coming 1 or 2 weeks. When is your second test? 28, 29, 30?